Hi everybody, in this video we're going to now calculate an F value from some raw data that I've made up just for this little scenario so you can see how the process works from start to finish. Again, I'm going to go through it kind of quickly, so feel free to rewatch portions or slow it down or whatever it's going to take, all right? But I'll get you to the final F value. Then in future videos we'll work on interpretation and figuring out whether it's statistically significant, then of course figuring out the post hoc analyses, but we'll do all that in the future. Okay, let's imagine a scenario, and again, this is entirely made up. There's somebody named Nadine. She's developed this new fertilizer. The fertilizer is designed to stimulate plant growth. So she now needs to come up with an experiment to figure out which amount of fertilizer is best to stimulate plant growth. In other words, she doesn't want to give too much into the soil because that might kill the plants, for example. We don't know. Or it might be that a little bit is not enough to actually stimulate plant growth. And so she wants to find the correct amount to really cause these plants to grow faster than they normally would. So what she does is get these different fertilizer amounts and applies them to the soil for, we'll say, 4 different groups, how about? And she plants the exact same type of plant in these 4 different amounts, fertilizer amounts of soil. And let's say that she wants to do not only one, because some of the plants will be slightly different, some of the seeds will be slightly different, and so to control for that, she wants to add several different plants to these types of groups. Then she measures these plants, she times them over several days to find out how long does it take them to arrive at a length of 6 inches, a height of 6 inches, we'll say, okay? So this is kind of what the data will look like then. She's got one group that receives only water and no fertilizer whatsoever. She's got 7 of these plants that she plants in that group. All plants receive the same amount of sunlight, all of that kind of stuff. Let's assume that everything else is the same. She's also got a group that receives only ½ ounce of the fertilizer in the soil mixture, okay? And this is how long it takes each plant to arrive at a height of 6 inches. Same thing, there's a 1 ounce group that receives 1 ounce of fertilizer and the 2 ounce group. Okay, so you can see how that works. So what she's got here is a total of 28 plants, or seeds, I could say, and she's divided them equally among these 4 groups, okay? Now what she needs to do is see which group, on average, had the fastest growth rate. That's essentially the point of the ANOVA. What's interesting about the ANOVA is it can compare all 4 groups simultaneously, whereas a t-test could control, or it could look at only 2 of these, or compare only 2 of these. So now let's again look at the equation. We've already seen it, but let's take a nice look. Here's the F equation, and again, I've arranged it so that we're talking about 4 group comparisons. As you can see up here, we've got all of the information from group 1, from group 2, from group 3, and group 4. Then this, of course, is everybody's information regardless of their group, and everybody's information regardless of the group, and so on, right? All of that. Okay, so the only thing that's really going to be different from any other equation we've looked at is we've got 4 groups, and our K value is, of course, going to be 4 as well because of those 4 groups. Now, I've decided just to rename these groups just ever so slightly to match our scenario. This doesn't hurt anything. Instead of calling it group 1, I've decided to call it the control group. So I've simply just called it the control group. And then the ½ ounce group, I've named half group, just to keep better track of it. And group 1, I'm deciding is the 1 ounce group, okay? And group 2 is the 2 ounce group, okay? Just to keep all of this arranged in my head. So anywhere where that mattered, I've changed and adjusted in this scenario just so we can better keep track of that. That's important for going forward. Okay, so back to the data. These are the original data that she obtained. So it took this long for her to finally reach all plants of 6 inches. It took her 16 days, or I'm sorry, 17 days until all the plants had reached 6 inches. Now, of course, the equation tells us that we're going to need to square every value that we have here, okay? So I've arranged the table to now allow that. So this is every every length of days that it took for plants to reach 6 inches, now squared over here, okay? This is just for the control group, and I've squared each of those values. 14 squared is 196, 15 squared is 225, 16 squared is 256, and so on. I've done that for all of those values. Same thing over here for the ½ ounce group. This is just every value squared over here. Same thing for the 1 ounce group, every value squared over there. If you're not sure, pause right here, do the math yourself. You can see what I'm doing, figure that out, all right? Same thing over here, 2 ounce group, every value is squared. 16 squared is this, 15 squared is that, 16 squared is that, and so on. Okay. Additionally, I'm going to need the totals from that. In fact, I actually don't need any of the individual scores anymore. I do need the totals of all of these. And so I've now added a row where you can see these totals here. So in other words, what I've done here is the sum of all of the days from the control group is 102. In other words, it took a total of 102 days for all of the plants to finally arrive at that, if I'm combining all of their days. Okay, same thing here. I'm combining all of the squared values. I've simply added up all the squared values to get 1,492. I did not square 102 to get at that value because that would be different. Okay, same thing here. Added up all those values, get it there. Added up all those values, get it there. So now at this point, all I really need is these total rows down here. And I also need to recall that we had 7 plants per group and we had a total plants of 28. Okay. All of that information I need to retain, and now I can plug everything into the equation where I need it. Now, one thing that we're going to need to make sure we do is to get the total sum of all of these. So in other words, the sum of all of the days that I have not squared. So of course, to do that, I simply take the total from the control group, which is 102, the total from the 0.5 ounce group, which was 65, the total from the 1 ounce group, which was 80, and the total from the 2 ounce group, which was 109. If I add all of those up, of course, I reach 356. So my total sum of all of the days that it took to arrive at 6 inches for all plants was 356 days. That's interesting because that's a whole year, but it doesn't matter. That's just a coincidence. Now I need to do the same thing for the squared calculations. Once again, we just take the sum of the squared group 1, or control, I should say the control group values, which was 1,492, with the half ounce group total, the squared values of the half ounce group, the squared totals of the 1 ounce group, and the squared totals of the 2 ounce group. So of course I simply add those across to arrive at 4,730. Okay, so in other words, the total sum of the squared values of every day, every amount of days that it took for, number of days I should say, that it took for me to arrive at 6 inches for each plant was 4,730. Okay, again, that is not 356 squared, so please do not mistake that. This is where you square each value first, then add them all up. Okay, and now we have absolutely everything we need to plug into our equation. So let's go ahead and do that. Here's the equation again that we're going to be filling in all of the values for, and then we simplify it and we just arrive at our F value. Now, of course, there's a lot going on here, but luckily a lot of these elements are repeated as we've discussed before, and so it won't take a whole lot of steps or repeated effort. So let's walk through this, how to plug everything in. Of course, the control group, the sum of the control group values was 102. And so we simply plug that in right there. That's all that it's asking for. And there were 7 observations per each group. And so each of these denominators down here, the little italicized ends, will be 7. So that's very easy. 65, of course, goes right there because that was the total of the half ounce values. The 80 is the total of the 1 ounce values, which goes there. 109 in the 2 ounce value. So all of that goes right there. Now, of course, this one is asking for the total sum of all of the values, which, as we said, was 356. Again, that's simply 102 plus 65 plus 80 plus 109, no problem there. And of course, our big italicized n means all of the observations, and we had 28 total observations. Of course, k in this instance was it's always the number of groups that we're comparing, and in this case, we're comparing 4 groups. So k, of course, is 4. Minus 1 is always standard there. Okay, and then down here, this, of course, is the squared. The sum of the squared totals. Okay, in other words, we square them first, then we take the sum. We figured that out by taking this plus this plus this plus this, which is of course 4,730. So that goes right there. And again, this little thing right here is called the correction for the mean. It's the exact same value right there. 356 squared divided by 28, of course, goes right there. And again, it goes right here, so we don't need to replug those in independently. You'll also notice that all of the values up here is the same thing down here in these brackets, so exactly the same thing. And again, big N is 28 minus 1, and then K minus 1 is again 4 minus 1, okay? So this is how everything plugged in quite nicely. Again, I moved through it fairly quickly. Please feel free to rewatch that portion. Now we simply simplify. We simplified. Okay, so let's go ahead and try this out. All we need to do is simplify here. I haven't done anything yet so far. This is just the exact same equation that I had on the previous slide. We're just going to simplify. So of course the order of operations dictates that we look inside parentheses first. Now, because we have fractions, we have a lot of implied parentheses, meaning that essentially whatever happens in the numerator is implied to be in parentheses separate from the denominator, except under maybe rare circumstances, although I can't think of an exception right off the top of my head. So within the numerator, we can look, for example, in here, and then we can see there are brackets already there, which is our essentially just parentheses. And so in that, we need to do the exponents first, as the order of operations dictates. So we're going to start with that kind of thing, okay? We're going to do all the exponents within brackets first. Here's how that goes. Of course, we square 102 to get 10,404. We square 65 to get 4225. Square 80 to get 6,400, and so on, right? Do the same thing with 109. That's great. Now, outside of these brackets, we also need to square 356. 356 squared is 126,736. Now look, you'll notice I also use this element down here. It's the same thing. 126,736 divided by 28. So I don't need to re-square that and re-square that, as long as I did it right the first time, okay? And then of course it's down here as well again. This little guy's called the correction for the mean, but of course that's a little beyond what we're doing right now, but if I ever refer to that, that's what it means. Okay, we can also do the parentheses down here in the numerator, because, or I'm sorry, in the denominator of the denominator, because that doesn't hurt anything. Elsewhere, the only thing that we could do here is what's in the parentheses. So 28 minus 1 is, of course, 27. 4 minus 1 is 3. Naturally, again, in the denominator of the numerator, which is right here, 4 minus 1, we can do that too without influencing anything else here. Okay, that looks like that's all we can do in this particular step. So I've done several things within brackets in one fell swoop. Now we're going to move on and continue to simplify. So again, I've moved that last equation just here on top so that we've got some room to work and refer back to it. As you can see, what I'm doing here now is division, because within the brackets, I next divide before I add across. Although technically, if you have the same denominator, it doesn't matter. You can go ahead and add across, then divide. It doesn't actually hurt anything. But if you have different denominators, of course, you have to divide first. Okay, anyway, if I divide first and then add across, well, I haven't added across yet, but I divide first, so 10,404 divided by 7 is 1,486.3. 4,225 divided by 7 is 603.6, and so on. So I've just divided each of those, and I'm keeping them there. Now, of course, 126,736 divided by 28 is 4,526.29. I maintain all of these operators in there. Of course, I'm just adding these across, so I haven't done that yet. I'm going to keep those operators there. Then I'm going to subtract this correction for the mean from those, okay? So that subtraction remains there. Can't do anything else with 3, so that remains there. Down here, same thing, okay? I'm going to take the 4,730 that I already had, and now look, I already arrived at this answer of 4,526.29 for the correction for the mean. That just goes right there. I don't need to redo the math, and it goes right here. Again, I don't need to redo the math. Same thing here. This all goes right here, okay? No problem there. So all of that remains there. In fact, technically, I don't actually need the parentheses inside of there because it's not going to make a difference at this response. But I've kept them there just so that you can see visually to keep them separate. All right, let's continue to simplify. Okay, so once again, exact same equation here. I haven't changed anything yet. All we're going to do now is add across and then subtract, and same thing. So we're not dividing anything yet. We need to arrive at these answers in the numerators of the numerator and the numerator of the denominator. All right, so again, we have here the total of this portion is 4,701.4. Then we're going to subtract that correction from the mean. Same thing down here, right? It's the exact same value that goes right there, 4,701.4, and we're going to subtract the correction for the mean. Okay, and this, of course, the difference between this and this is 203.7. So we'll need to do all this. This is, of course, going to be the next step. We're just going to figure out the answer to that and then continue on with this before we do any division. So let's do that next. Here we go, exact same equation, haven't changed anything. Here's the difference between the numerator of the numerator is 175.14. Really quickly, this is called the sum of squares for the between groups variance. I'll talk about that more when we talk about source tables, but don't worry about it right now. The sum of squares for the between groups difference, and we haven't divided it by the degrees of freedom, which is what this is, the degrees of freedom for the between groups variance. This, of course, is the total variance, And this is the between groups variance, as you can see once again, because it's the same value. So once we subtract there, we get something called the within groups variance, or the sum of squares for the within groups variance, I should say. This is, of course, the degrees of freedom for the within groups variance. All right, so here's what we have now. We have a total mean squares is what that is. This becomes the mean squares of 58.38. That's just 175.14 divided by 3. And of course, the difference between 203 and 175 gives us a sum of squares for the within groups variance of 28.57. We're then going to divide this, of course, by that. So 28.57 divided by 24 gives us the mean squares for the within groups variance, which is 1.19. Now, again, I'm talking about a lot of terms here. Again, you don't need to worry about that too much right now. I just like to refer to them here. We'll talk about them more when we get to the source table. So now at this point, we simply divide 58.38 by 1.19. Very simple. And we get to 49.04. Now, if you arrived at something slightly different, or if your calculator arrived at something different, or Excel, for example, I've rounded ever so slightly just to save some space here on the slides. But it should be very close to 49.04 is what you get, okay? Now, we need to interpret this. We need to find out if this is statistically significant and find out what we know from this and what we don't know. So we'll start doing that in the next video, and I will see you then.